enjoying what you're doing. That's the aim of today. Okay. Alrighty, let's get started then. We're still on chapter 3, section 3.3, simultaneous equations on graphs. We've talked about solving simultaneous equations and solving quadratic simultaneous equations. And now we are going to be graphing them. So think about those solutions we're coming up with for the quadratic simultaneous equations. Those solutions represent where the straight line and the quadratic intersect. Okay, so you can represent the solutions of simultaneous equations graphically at every point on a line or curve. As every point on a line or curve satisfies the equation of that line or curve, the points of intersection of two lines or curves satisfy both equations simultaneously. The solutions to a pair of simultaneous equations represent the points of intersection of their graphs. Here's an example. On the same axes, draw the graphs of 2x plus 3y equals 8 and 3x take y equals 23. So they are two straight lines, obviously. Or maybe not obviously, but when there are no squared terms, they're going to be straight lines. And I have some graph paper here because I have a feeling I'm going to be doing a lot of graphing. But they've already done this example for us. Okay, so here they've graphed the two straight lines, and then where they intersect is the solution. So that intersection is at 7, -2. So x equals 7, y equals -2. So remember, we were solving these algebraically. Now we are going to be able to solve them graphically as well. Then we have an example of a quadratic inequality. For these, you need to be able to sketch the quadratic and then the straight line, and where they intersect will be the solution. Now it doesn't tell us how we should be sketching the quadratic, and there's a couple ways you could do that. You can either draw a table of values or use the method we used in chapter 2, where we found the minimum and the roots and then we sketched it. Can you go through past AS papers? Yes, eventually I will be going through last year's. So here it says there are two solutions. Each solution will have an x value and a y value. Check your solutions by substituting into both equations. Now I'm wondering how we should be sketching the quadratic, and how accurate we need to get the sketches. If we just plot the minimum and the points of intersection, this point here, if we were sketching this particular graph, this point could be way off. So rather, for this example, I would probably want a table of values. In order to get an accurate point there. So maybe they give us another example. So anyways, it goes on. It says the graph of a linear equation and the graph of a quadratic equation can either intersect twice, intersect once, or not intersect. So maybe you can see that this line doesn't have to be going through the quadratic. It could be out here somewhere, or it could just be touching the quadratic, and we could get these three situations. After substituting, you can use the discriminant of the resulting quadratic equation to determine the number of points of intersection. So remember, when we were solving these algebraically, we substituted the linear equation into the quadratic equation and then solved it. And here we're going to be using the discriminant to see how many times that straight line intersects with the quadratic. Okay. So for a pair of simultaneous equations that produce a quadratic equation of the form ax squared plus bx plus c equals 0, b squared take 4ac is greater than 0 has two real solutions. We've already talked about the discriminant. That will be where the line intersects the quadratic in two places. B squared take 4ac equals 0 has one real solution. That's where the line is tangent to the quadratic, just touching it once. And b squared take 4ac less than 0 has no real solutions. The line will not be intersecting the quadratic at all. Okay, another example here. The line with equation y equals 2x plus 1 meets the curve with equation kx squared plus 2y plus k take 2 equals 0 at exactly 1 point. Given that k is a positive constant, find the value of k. For this value of k, find the coordinates of the point of intersection. Okay, key piece of information there, or the key I can't speak today. The key piece of information is that they intersect at 1 point. So that's going to be this situation here, where b squared take 4ac equals 0. So what we need to do in this situation is to take, essentially solve these algebraically as we have been doing. So we take this value of y, substitute it into this equation, and then simplify. We get a quadratic in terms of x, and then we use the discriminant to solve for k. And given that k is a positive constant, we can say then that k equals 2. I hope the microphone's okay. If somebody could let me know. Hello, Philip. Part B, for this value of k, find the coordinates of the point of intersection. So then you substitute the value of k back in to the original quadratic here. So 2x squared plus, this quadratic where we've substituted in. So we substitute that value of k into this quadratic here and then solve for x, and that will be the only solution because we get x plus 1 multiplied by x plus 1 equals 0. So we get one solution there. So the point of intersection is -1, -1. Thank you. Thanks for letting me know. Okie dokie. Alright, so I still kind of haven't solved this mystery of how should I be graphing this quadratic. As I said, there's two ways we could do that. We could find the points of intersection and graph it that way, or we could create a table of values. Personally, I feel the table of values is going to give a more accurate graph, but we've really only talked about, but I feel like that's suggesting that we should be finding the intersection points. This example isn't too helpful in that it doesn't really kind of give any hints as to how we should be sketching that quadratic. So anyways, let's get started. on exercise 3C. We're starting off with some linear simultaneous equations. So part I is asking to draw the graphs for each pair of equations on the same axes and then find the coordinates of the point of intersection. Okay, so let's see. I'll just do one of these, I think, just to give the idea of what we're doing here. All right, this first line has a y-intercept of -5, 1, 2, 3, 4, 5, and a gradient of 3. So this would be up 3 across 1. So my first line looks something like this. This is y equal to 3x take 5. Hello, the omnipotents. Welcome. Y equals 3 take x. That's y-intercept of 3 and a gradient of -1. So that would look something like this. And then we have our point of intersection. So for A part I, well, that's the graph. So actually for part 2, we want the solution. That will be 2, 1. Okay, so the point of all of this isn't immediately obvious with examples like this. You would say, well, isn't solving it algebraically, doesn't that make more sense? Doesn't that give a more accurate answer? The point is, down the road, this can be a helpful method to solve more complicated simultaneous equations, or give an idea of what the solution should be. So even though in reality no one would really do it this way for 2 linear equations, you might do it for, you know, I don't know, like maybe 2 cubic equations or something. It might actually be easier to graph them rather than to try to solve it algebraically. So that's kind of the point. Anyway, so that's the idea behind this. You can have a go at B and C as well if you like, but I'm going to move on to question 2. 2a says, use graph paper to draw accurately the graph of 2y equal to 2x plus 11 and y equal to 2x squared take 3x take 5 on the same axes. Use your graph to find the coordinates of the points of intersection. Okay, so straight on to the quadratic then. And I'm going to face this decision of whether to graph the quadratic with a table of values or not. So let's write down the equations. I've got 2y equal to 2x plus 11 and y equal to 2x squared take 3x take 5. And I want to graph these. I'm going to write this in gradient intercept form. I personally find that easier. If you don't need to do this, then great. Okie dokie. So we're graphing these two. I may end up shifting these axes depending on what the graphs look like, but we will see. So how to draw the quadratic. How to draw the quadratic. I really just want to do a table of values. I feel that's the most helpful way to do it. So that's what I'm going to do. So the table of values for the quadratic. We can go from, say, -3 to 3. And there might be situations where this is not practical at all. It might just be easy to get the intercepts. Yeah, so yeah, I could find the vertex in the intercepts. I don't know. The problem with that is, like I was pointing out earlier, in this example, if I just get the minimum and the intercepts, this point, I could be way off with that point there. Okay, that's not going to give me an accurate intersection of the two graphs. So wouldn't I rather want each point on the quadratic? I don't know. This has always been kind of a strange subject for me, like hard to sort of justify doing it this way, justify graphing them. Even though I kind of said why we do this, it's still a little bit confusing. But all right, so here's what I'm going to do actually. I'm going to do it with the table of values, and then I'll do it with the minimum and the intercepts, and then see how we go. Okay, so the table of values. Hello, hello. And now I'm feeling like this is a much slower way to do it with the table of values, because I have to substitute in each one, get a value. So now I'm thinking that it would be better off to do the intercepts and the minimum, just due to the fact that it's way faster. But anyways, let's just see. So plugging -3 in, we get 18 plus 9 take 5. This is 22. Oops. Okay, and if I make small errors with these, then please feel free to correct me. 2 squared times 2 is 8, plus 6 take 5. This is 9. Excuse me, I just have to go and shut one of my windows. Okay. Just got 9 for -2. -1. This would be 2 plus 3 take 5. That's 0. Plug 0 into this, we get -5. Plug 1 in, we get 2 take 3 take 5. -6. Plug 2 in, so this is 8. Take 6 take 5. negative 3, and then 3, plug 3 in, we get 18, take 9, take 5, 4. Alrighty. It becomes obvious once you plot it if you've made any mistakes anyway, so I'm not going to bother double checking. I'll check when I graph it. So firstly, let's graph this quadratic, see what it looks like. So negative 3, 22 will be way up here somewhere. So, okay, let's just say it's, you know, way up there somewhere. Negative 2, 9, 2, 2, 4, 6. Oh, this only is up to 8. I didn't realize. Okay, so let's say the scale on the y-axis then is 2. So 2, 4, 6, 8. 9 would be here. Negative 1, 0. 0, negative 5. 1, 2, 3, 4, 5. Oops. This should be here. 1, 6. Oh, whoops. I also changed the scale on the y-axis, didn't I? So a couple of mistakes here. 0, negative 5 would be here. 1, negative 6 would be here. 2, negative 3 would be here. And 3, 4 would be here. So they kind of look okay. The minimum, now I kind of am curious what the minimum is, where it is. So we can do negative b on 2a to find that. So 3 on 4. And then this looks kind of wrong. Or maybe not. One. Now I feel like I've made a mistake in here because the graph looks a bit off. So, maybe not. Okay, so I'm just going to go ahead and sketch this and see. So, I guess it would look something like this. Okay, so that's the graph of that quadratic, and I believe we could also factorize that. So what would the factors be to make negative 3? So I need factors of negative 5 and 2. This is just to check the intercepts. So 5 and 2 should make 3. So 2x and x, and then 1 and 5. Is this going to work? So then we'd have a negative 5 plus 2. So the x-intercepts are 5 on 2, about here, and negative 1. Okay. Now the straight line is 5.5. Sorry, the y-intercept is 5.5. Be about here. And the gradient is 1. This scale is really going to mess me up. So up, if I go up to, where am I? So that would be Let me just draw some numbers in. This would be 2, 4, 6, 8. So if I go up 1, it'll be about here. Okay. Ooh, these are going to be rough solutions. Hello, hello. So now we need to find the points of intersection. You can see here why I'm hesitating a little bit is because look at this one. What is this point going to be? Well, actually, maybe it's not so bad. This is possibly negative 1.5, and this might be 3. And this one, maybe it's, so this is 10, maybe it's 11 and 3.5. Oof. And then we can check those by substituting them in. So they have to satisfy both equations. So if I used negative 1.5 and 3, what would we get here? We would get 6 equal to, no. So if y is 3, x would have to be, what, negative 2.5. So we'd have to get negative 5 here. So what is x is if this is negative 5? Yeah, negative 2.5. So this is way off then. Oh, this line is way off. I don't know why I've drawn it there. Oh yeah, no, sorry. The y-intercept is 5 and 2. I was thinking it was 11. So the line is correct. The quadratic, I believe, is correct. Maybe this y value is wrong. This is hard sketching this. I mean, maybe on paper it's easier. on this software it's quite difficult. All right, what can I do here to help me to solve this more accurately? I could have a bigger graph. Yeah, okay, so I need the intersection points and mine are clearly off, so I feel like my graphs are wrong or my sketch is too inaccurate. So what I'm going to do is just change this scale back to 1:1, and then maybe I get some solution. Okay. All right, so I'm going to plot from -2. 9 was up here. -1, 0 is still there. 0, -5. 0, -5 is now here. 1, -6 is here. 2, -3 is here. And 3, 4 is here. Are we, maybe they're expecting us just to do this with some graphing software. Although this does come up in exams. So you are expected to be able to do this accurately. And let me just think. Yeah, I think usually they give you the table of values. That's usually how they suggest you graph the quadratic. It's just confusing in this chapter. They don't like give any kind of indication of which method is most helpful. Okay. Then this is 5.5. And the gradient is 1. Okay, that looks more promising. This point here definitely looks, oh, it was 4. So that's definitely a 4. This is a -1.5. What about this one up here? This looks like a 3.5 and a 9 by the looks of it. All right, let's see. So plugging -1.54 in to the first equation, we would get 2 times 4 equal to 2 times -1.5 plus 11. Is this true? This is 8, and on the right hand side, I have -3 plus 11. Great. So this point is correct, at least for the straight line. And then for the quadratic, actually, how do they suggest to do that? Yeah. Plug them into both. So then plugging those 2 points into the quadratic, y equal to 4, x equal to -3 on 2, we would have 2 times -3 on 2 all squared, take 3 times -3 on 2, take 5. Is this true? Just move this down a little bit. Let's see, so all of this needs to equal 4. This is 2 times 9 on 4 plus 9 on 2, take 5. And this is like 9 and 2 is 4.5 plus 4.5. That's 9, take 5, which is 4. So that is working as well. So this is a definite solution for the equation, -1.54. And the other one I said was 3.59. So let's see. Plug them into the straight line equation. We have 2 times 9, and on the right, by the way, I wouldn't suggest doing it this way. I wouldn't suggest setting them equal to each other because maybe you're wrong. So you can set it out differently to this. But these are basically just rough notes. These are just checking that your solution is correct. We have 2 times 9 equals 2 times x. X was, for the second solution, was 3.5, so 2 times x will be 7 plus 11. This is 18 equals 18, so that works. And then we need to check it for the quadratic. For this, we have 9 equal to 2 times 3.5 squared is 7 on 2 squared, take 3 times 7 on 2, take 5. So all of this needs to equal 9. Here we would get 49 on 2, take 21 on 2, take 5. And that is 20, what? Oh yeah, yes, this is 28, sorry, 28 on 2, which is 14, take 5, and this is equal to 9, so that works as well. So after all of that, I have my two solutions of -1.5, 4, and 3.59. I'm just going to go searching for a minute, looking for an exam question that involved graphing simultaneous equations. So just bear with me for a minute if I can find one. I seem to remember doing something similar at some point. Although I might even just be thinking of the GCSE exams. perhaps they don't bother putting questions like these into the final A-level exams, which begs the question, why would we bother learning this topic? Okay, so there's an example of an ellipse and a circle intersecting, but I still solved that algebraically. Okay, so there's examples like this. Where they kind of suggest that you solve this graphically. Although, this is from 2019 papers, by the way, although I solved these algebraically anyways, so okay, I'm going to keep searching. Now, I'm not saying here that this is not an important topic. I'm just looking for examples in the exams where this actually comes up and what those questions actually look like. Okay, so bear with me until I can find an example. Maybe the mock papers. I'm sure I've seen something like this. I just can't think. Okay, here's another example of graphing functions and using that to solve an equation. Although again, I'm yet to see an example that is not also possible to solve algebraically. So, what to suggest here? Or how to approach this topic? That's kind of what I'm wondering. Here's an example with a circle, and they give you some conditions on the lines. But again, this was largely solved algebraically. I mean, the graph helps to understand the problem, but the actual solution you get at algebraically, as I said. Okay. I'm not sure I'm going to find anything. Graphing simultaneous equations in the exams. Is there any examples? Is there any recent examples? Alrighty. Okay. Alright, I'll use this question as an example. Okay. So the point I'm going to try to make here is that we did all of this to solve these two equations graphically. So we have a quadratic here and a linear equation here. And we did a whole bunch of work to get the solutions for these two things. And arguably, it would be faster to solve this algebraically. What's important is to get an understanding of the graphical method as well. Even though generally you probably solve this algebraically, just getting an understanding of what you're doing when you're solving this graphically is important due to questions like this one here. So this question was involving this equation, cosine x take 2x take a half equals 0. And you had to show that there was only one solution to this equation. So by understanding this process of solving this graphically, you're able to understand how you might go about solving this problem. So the approach to solving this particular question was to let cosine of x equal 2x plus a half. So the cosine graph, which is here, for this equation was equal to the straight line 2x plus a half. And then because you understand this process of solving equations graphically, you can say, well, the solution to that equation, cosine equals 2x plus a half, would be where the cosine graph cuts or intersects with the straight line 2x plus a half. And once you draw that line in, you see there's only one point where they intersect, and then you have your reason for there only being one real root. So that's my point really there, is that although we're practically probably not going to use this method to solve quadratic simultaneous equations, we will need this understanding for different types of questions. Okie dokie. Alrighty. I'm not sure I want to do another one of those questions right now. They're quite time consuming. Hello Google account. These are all quite similar, it looks like. Here we have a straight line and a quadratic. Again, quadratic straight line. Here we have y squared equals 2x squared take 17. That might be interesting to have a go at. Okay, so question 5. What do you think this graph is going to look like? Anyways, we have the equations y equals x take 4 and y squared equals 2x squared take 17. I wonder. What to do with that equation? Initially I was thinking it was going to be a circle, but this is, you get y squared take 2x squared equal to negative 17. Or actually, let's write it as 2x squared take y squared equal to 17. And that's not a circle, right? Because we have a coefficient of x squared. Oh. No, I was going to say we could use the difference of two squares, but I'm not sure that helps. Do we just do another table of values? Possibly. Or it doesn't even say to graph them. It just says to find the coordinates. So do we just solve this algebraically? No, it's not a quadratic. It doesn't say to graph this one, so... But this whole section is on graphing. I'm a little bit stuck. Interesting. Curious what this graph looks like. No, you haven't missed much. I've only done 2 questions so far, actually. And I had a bit of a spiel about why we care about graphing quadratic simultaneous equations, but that's about it. Okay. So, it's like a hyperbola type of shape. It's like the inverse of an ellipse. Weird. So how I don't know what to say. This whole section is supposedly on quadratic simultaneous equations, although I guess it says simultaneous equations, so it doesn't have to be quadratic. All right. So what I'm going to do with this one is do it algebraically, and then maybe that's impossible. Maybe I can't solve it algebraically, and then we're going to have to graph it. So let's see, let's try to do this algebraically and see what we get. Yeah, so substitute that x take 4 in for y. So let's just label them. This will be equation 1, equation 2. So taking equation 2, we would get x take 4 all squared equal to 2x squared take 17. And then x squared take 8x plus 16 equal to 2x squared take 17. And then x squared plus 8x take 33 equal to 0. No, this has solutions. This has 2 solutions, unless I'm wrong. So this would be x and yeah, x take 3 and x plus 11 equals 0. And then x equals 3 or x equals negative 11. And then getting the solutions for y, if x equals 3, y equals negative 1. If x equals negative 11, y equals negative 15. Okay. Now I'm wondering what to think at this point. If anything, these questions are an argument against graphing simultaneous equations. Like, look how easy this is algebraically, and then how difficult this would be to graph this function, or this equation, sorry. I don't know. This is a bit of a dud section, I think. And I guess this is a place to point out textbooks are not always perfect, you know. They're written by humans, and you know, sometimes it's not clear what they intended with a particular chapter. Like, what are they expecting us to do here? Are they expecting us to solve it algebraically? Are they expecting us to graph it? What's the point? Anyways, I'll try to stop rambling and just get on with it. I might have a look at the rest of these later on and try to maybe put a more coherent, or put the questions together in a more coherent manner. So it makes a bit more sense. So I'm going to move on to section 3.4 now, leaving those questions for later. But I do have to check these answers before I move on. So if you want to give any of these questions a go, feel free. And I'm going to check the answers to the ones I've done now. So this was exercise 3C. Okie dokie. 3CA was 2, 1, and the graph there. Um, 2B was 3.59 and negative 1.54. 5 was negative 11, negative 15, and 3, negative 1. And they don't give a graph for that one, so I'm guessing they just wanted it algebraically. I am confusion. Alrighty. Linear inequalities. Let's get rid of this one. Section 3.4, linear inequalities. You can solve linear inequalities using similar methods to those for solving linear equations. The solution of an inequality is the set of all real numbers x that make the inequality true. The set of values of x for which, find the set of values for x for which 5x plus 9 is greater than or equals to x plus 20. So yeah, as they say, solve it like an equation. So you can use all of the algebraic rules you already know, like subtracting things from one side or the other, dividing by things. The one thing that you need to watch out for is dividing by a negative. So divide both sides by -3. You need to switch around the inequality. So whenever you multiply or divide by a negative, you need to switch the inequality. Actually, let's just talk about why that is for a second. So let's say you have a number less than -2. So let's draw a number line. This is 0, 1, -1, -2. So at this point, x is this. Remember, when you draw these on a number line, you have an empty circle for less than. If I then divide by -1, I would have negative x on this side and 2 on this side. 2's over here. And x is a negative number. So if we divide through by a negative, this would then be a positive number larger than 2. So we need to flip that inequality around. And kind of the way I think about it is, you are, whatever number you have, you're changing its sign. So if you have a negative here, if you multiply divide by a negative, it's going to become a positive. And then it belongs on a different area of the number line. You need to, rather than less than, it's now going to be greater than. Anyways, that's a bit of a side note as to why we flip the inequality sign around. But I'm sure that you're all okay with that already. Okay, so they give some examples. If we have 5x plus 9 greater than or equals to x plus 20, solving for x, you could subtract the x from the left-hand side, subtract the 9 from the right-hand side. We get 4x greater than or equals to 11, and then x greater than or equal to 2.75. Pretty straightforward stuff. And even if you have brackets, just expand the brackets, simplify, and you'll be fine there. You may sometimes need to find the set of values for which two inequalities are true together. Number lines can be useful to find your solution. For example, in the number line below, the solution set is x greater than -2 and x less than or equals to 4. Here, the solution sets are x less than or equals to -1 or x greater than 3. Okay, so that's important to look at that language they're using as well, and or. When it's two separate ones, it's or. When it's between a certain range, it's and. In set notation, x greater than -2 and x less than or equal to 4 is written x semicolon -2 less than x less than or equal to 4. Or alternatively, x semicolon x greater than -2 intersect x less than or equal to 4. Okay, x less than or equal to -1 or x greater than 3 is written as x less than or equal to -1 union x greater than 3. Okay, I might actually make a note of that because I'm hopeless at remembering this kind of stuff. So x greater than -2 and x less than or equal to 4. This is written as x colon -2. X between -2 and 4. Okay, so that's how that one's written. And then we have x less than or equal to -1 or x greater than 3. So this is a separate, these are two separate ranges. So x could be in this range below -1 or greater than 3. So that's why we say or. It's either in this range, this domain, this set of values, or in this set of values. It obviously can't be in both. Whereas in this set of values, it's between two numbers, so it's the set of values is enclosed within -2 and 4. So we say it's between those two. So we say the solution set is x greater than -2 and x less than or equal to 4. And then this one is written as two separate ones. So x is x less than -1. And this is a union with x greater than 3. Remember what union was when we talk about set notation? Union, that essentially means or in sets. And you can think about it as a Venn diagram. I have a video on Venn diagrams talking about this notation. It was this area in different color. It was this area in here. So it's one or the other. Actually, but in this case, they would not be intersecting. There's no intersection between those two ranges. So I've drawn that incorrectly. This should be like this. So this would be like a Venn diagram with two separate sets that are not overlapping. So it's either in this one or it's in the other one. Okie dokie. Just a small note on the notation we're using for set notation, because sometimes exams will ask you to use this notation specifically. They'll say give your solution in set notation, and if you don't use the correct notation, you actually lose marks. And also, if you go on to study mathematics at university, it becomes all the more important to use the correct way of writing things, because you know your professors will be upset. If you eventually want to go on and be a mathematician, then you want to be able to publish papers, and then if you want to be respected, I guess, I don't know, I'm not a mathematician obviously, but I mean, I've never published a paper, but I guess if you don't write it correctly, then I don't know, all the mathematicians will judge you or something, I guess. But anyways, set notation. I'm rambling a lot today. Find the set of values of x for which 3x take 5 is less than x plus 8 and 5x is greater than x take 8. We have two ranges, and therefore, two inequalities. Therefore, it needs to satisfy both. So here they give the answer as x between -2 and 6.5. There they're not using the set notation, but they say in this note here, in set notation, this can be written as x colon -2, x colon x between -2 and 6.5. So basically, the only difference there between the inequality and the set notation is they're just adding the brackets around it and the x and the colon. Okie dokie. Well, let's just do a couple of these inequalities, just to give an idea. So if you've got 2x take 3 less than 5, pretend like it's an equation, so add that 3 onto the right hand side. We want to get that x by itself, divide by 2, we get x less than 4. For b, I'll just do 2 of these. Actually, let's do one with a negative, just to show when you need to be careful. So let's do f. Although that still doesn't have a negative. Where is one where we need to divide by a negative? None of these. Oh. Okay, so let's just do E. 15 take x greater than 4. Now for this one, you can either add the x to the other side, so you get 15 greater than 4 plus x, and then subtract the 4, so x is less than 11. Okay, let's do it slightly differently. Let's say negative x is greater than 4 take 15 is negative 11. So negative x greater than negative 11. If I divide through by negative 1 there, I'll get x and 11, and I also need to flip the inequality, so it will be x less than 11. Just demonstrating why the negative is important. So, okay, so there's a couple linear inequalities. Let's do a couple from question. There's some quadratics in here. So now I'm confused. I thought this section was on linear inequalities. Let's see. Do they all cancel out? Oh yes. So this looks like there'd be some quadratics, but actually all of the x squared terms cancel each other out. So that's still linear inequalities. So let's do some from 3. 3 multiplied by x take 2 greater than x take 4, and we have another one, 4x plus 12 greater than 2x plus 17. So actually, let's I'll move this down a little bit. So we need to solve both of these inequalities. Let's do this one on the left first. This will be 3x take 6 greater than x take 4. Then 2x greater than 2, and then x greater than 1. So that's one set of, or that's one inequality. And then the other one, we would get 2x greater than 5. Not 15, 5. And then x greater than 5 on 2. It says use set notation. So here the number line can help. Here's 1, here's 2.5 or 5 on 2. So we have both of these greater than. So really the only inequality we care about is the fact that x is greater than 1. We don't actually need to worry about this 5 on 2. I'm just double checking that I've done it correctly. So I added that 6, took that x. Yes. So yeah. So if we're writing this as set notation, we say do we say solutions? What's the word we use? Yeah, we say the solution is, actually, how do we write it? Possibly we can just give our answer as this. Okay, so that is the solution, x greater than 1. Let's do one more. Or maybe we say solution set. I think that's the correct language to use. Part B, 2x take 5 less than x take 1, and 7x plus 1 greater than 23 take x. This is x less than 4, And over here we have 7x plus 7 greater than 23, take x. And then 8x greater than 30, and then x greater than 30 on 2 on 8, 15 on 4, which is just less than 4. So 3 and 3/4. Okay, so the number line is going to help with our understanding here. So we have a inequality of x less than 4, an empty circle to show it's just less than, not less than and equals to. And then x greater than 3 3/4. Let's just say it's here. So the solution set is going to be between, so greater than 3 3/4 and less than 4. Oh, oops. I made a small calculation error there. Apologies for that. This should be 23 subtract 7, not 23 plus 7. So 23 take 7 is 16. So x is greater than 2. Okay. So these are my two inequalities. And remember how we wrote this? We had those funny brackets, then x colon x between 2 and 4, and then the brackets again. Okay, so let's just go ahead and check the work we've done so far. If you want to do any of those other questions for extra practice, go ahead. Okie dokie. We're on to 3D. X less than 4, x less than 11. Oh dear. So I've clearly made an error here. This is why you always check the work you've done. If x is greater than 2.5, it can't also be greater than 1. So we have to take the greater value there. So we, whoa. Yeah, so clearly an error there. If x is greater than 2.5, that's going to be the solution set, right? It can't be less than 2.5. So x greater than 1 was clearly an error. Bit of a blind spot there. Okay. But the next one we did get correct. X between 2 and 4. Alrighty. Okay, linear inequalities, not too bad. Just don't make mistakes like that, I guess. Alrighty, if you are in the live stream, let me know. Should we move on to quadratic inequalities or do this challenge here? If nobody says anything, I'll be moving on and leaving that one for you to have a go at if you want to. I think that means to do the challenge. Okay. Oh, you say if I feel like it. That's nice. I don't want to do it, but let's see. I was hoping to get through more than this today, but I guess I'll have to leave the rest for tomorrow. Okay, so we have these solution sets. X plus x on 2 plus 1 less than or equal to 3. It's okay, I don't mind. And 2x take 1 greater than 11. Oh boy, they tell us that given that A intersect B union C equals x between P and Q. Need a bit more space here. Given that A intersect B union C is equal to x between P and Q union x greater than R, find the values of P, Q, and R. Okay, this isn't too bad. It looks complicated, but really it's, I believe it should be following similar steps to what we've already been doing. So for A, we could say 3x plus 5 is greater than 2, therefore 3x is greater than negative 3, therefore x is greater than negative 1. Okay. For B, x on 2 plus 1 is less than 3. So x on 2 is less than or equal to 2. Therefore, x is less than or equal to 4. And for C, we have 2x take 1 greater than 11. 2x greater than 12, so x is greater than 6. Now what? B union C. Okay, so let's have a look at these inequalities B and C. So x less than or equal to 4 and greater than 6. So possibly a number line is the easiest way to think about this question. Greater than 6 is this way. Less than or equal to 4 is this way. And x greater than -1 is this way. Just double check I've got these correct. So this was -3, -1. This was 2 times 2 is 4. Yeah. So B union C, that's just these two sets. And then A intersect that would be this range, I believe, right? And also this range here. Okay, so again, this was A, this was set A, this was set B, and this was set C. So in order to satisfy all of those sets, basically that's what we're trying to do. Excuse me. Domain, yeah, I keep saying range when I mean domain. Thanks for picking me up on that. In order to satisfy all of these sets, we would have x between -1 and 4. Union or x greater than 6. So in this case, P is equal to -1, Q is equal to 4, and R is equal to 6. Alrighty, not too bad. That question looks scary because of all of the notation being used, but actually all it's asking you to do is to find those 3 inequalities and then write the set notation that satisfies the 3 inequalities and then find the values of P, Q, and R. Let's go ahead and check that we got the right one. After all that, maybe I'm completely wrong. Okay, so we did it correctly. Okie dokie, quadratic inequalities. Not today. But I have a video on quadratic inequalities if you do want to go ahead and check that out. Actually a fairly recent video I made on quadratic inequalities. Also, I believe I put some exercises below that video. Actually, let me check. Quadratic inequalities. Oh no, thank you for joining in. My loyal viewers. I appreciate the 4 of you that are here right now. I appreciate each and every one of you. You might think, okay, why am I live streaming for 4 people? But actually it's really motivating to have some company while I'm studying this textbook. Otherwise I would get bored quite quickly. So thank you for coming. Okay, doesn't show up when I search quadratic inequalities. That's rude. Come on, YouTube. Actually, let's see. Hello, Emma. GCSE Maths Tutor has also a video on quadratic inequalities. Exam Solutions has a video on quadratic inequalities. 2 good channels you could check out. Here we go, quadratic inequalities. There's an ad. In this video I'm going to be taking a look at quadratic inequalities, and I'm going to do 4 exam style questions. So the first one here says n is an integer. Yes, I did put some problems in the description. 1 and 2n squared take 5n is less than 3. It's positive, happy. How could we represent the is not a valid answer? But they are kind of GCSE level questions. Okay, for now I'll hang around for about another 10 minutes. If you have any questions, good afternoon, AJ Maths. So is everyone just finishing year 12? I'm curious as well. Felix just here for fun and to torture me with your trig identity questions. I was looking in the exam papers from last year, and I saw a question similar to that one that you had yesterday. Where is it? Now I can't find it. Of course, whenever you want to find something, you can't find it. Nope. Anyways. Must be in the mock papers. Let's see. So, does anybody have any questions? Any maths questions? Or anything else? Here it is. Kind of similar, but not really. Yours was 1 plus sine over cosine. A little bit different. Alrighty. Well, I think that's it then. See you tomorrow. Have a good afternoon. Enjoy whatever it is you get up to. Bye for now.